Have you ever, like, stopped and thought about what makes a thing a thing? Like, what makes a flame or a rock a rock? It's a question that seems super simple on the surface, but then it gets really complicated.
Yeah, absolutely.
When you actually start to, like, think about it.
It's a question that's puzzled philosophers and scientists for centuries.
Well, on this deep dive, we're talking about this paper that has this really cool new way to think about defining objects. And it uses something called Dynamic Markov Blankets.
Right.
Which sounds kind of complex, but the idea is actually pretty intuitive.
It is, yeah.
I think.
Think of it like a cell membrane.
Okay.
It's a boundary that separates the inside from the outside.
Okay, so it's like we're drawing a line in the sand.
Yeah.
And we're saying this is the object and this is everything else that's surrounding.
But what's really interesting about this paper is that they're defining objects not just by like their physical boundaries, but by the way information flows across those boundaries.
Oh, yeah.
So it's like a fingerprint based on how something interacts with its surroundings.
So it's not just about what an object is,
right,
but what it does.
Precisely. And this lets us actually define objects that maybe don't have like a fixed boundary. Like a flame.
Yeah, that's a great example.
Yeah.
Because a flame doesn't have a fixed shape, it's always moving.
Right.
And like flickering and changing.
Yeah, and the paper uses this example of a burning fuse.
Okay.
And the boundary is not the physical edge of the flame, but the point at which the fuel is igniting.
Okay.
So the point where the information about burning is being transferred.
So where it's actually happening.
Yeah, exactly.
Okay.
So that's the boundary.
What I thought was really cool was that the environment might be a better indicator of where the flame is than the flame itself.
That's one of the really fascinating insights of this approach.
Yeah.
You know, it suggests that the interaction between the object and the environment
is as important, if not more important, than the object's internal properties.
So it's like to understand the flame, you need to understand the air around it.
Exactly.
The fuel.
The wind.
Yeah. The shape of the candle.
Yeah.
Okay.
Everything.
All of those things.
It's a shift in perspective.
Yeah.
From looking at objects in isolation to seeing them as part of this larger system.
Okay.
And this connects to a concept called the free energy principle.
Okay, so the free energy principle, we know this is a big idea in like physics and biology.
It is.
But for our listeners who maybe haven't heard of this, can you give us like a quick breakdown?
Imagine that the universe is constantly trying to minimize surprise.
Okay.
So it wants things to be predictable, wants things to follow certain patterns.
Okay.
And the way that systems do this is by maximizing their caliber.
Okay, caliber.
Yeah.
What's that?
Think of it as a measure of randomness or possibilities.
So a system wants to be able to do as many things as it possibly can, but within the constraints of its boundaries.
Okay.
Its Markov blanket.
Got it.
You see.
So it's like this balance of wanting to be free, but also needing to stay within some kind of rule or structure.
It's this dance between wanting to be unpredictable, but also staying within certain limits to maintain its identity.
Okay.
And it's this dance between maximizing caliber and adhering to these boundary constraints that gives rise to what we call an ontological potential function.
Okay, ontological potential function.
Yeah.
That sounds pretty intimidating.
It's a mouthful.
Can we break that down?
It might sound complicated, but essentially it's a mathematical function that describes the most likely way a system will behave given its Markov blanket, given how it interacts with the world.
So it's like a set of rules that determine how an object exists and interacts.
It's a blueprint for being a certain type of thing.
Okay, so this is all super interesting.
Yeah.
But I'm curious, how does this idea of defining objects by their interactions through these Markov blankets relate to like the bigger picture? Like how does it relate to things like the origins of life or artificial intelligence?
That's where it gets really exciting because this framework allows us to see life and intelligence in a whole new light as emergent properties of information flow and interaction with the environment.
I can't wait to unpack that more.
Me too.
But I think we might need a little bit more time to digest this ontological potential function.
It's a lot to take in.
Yeah.
It is.
So listeners, stay tuned.
Yes.
Because this deep dive is just getting started.
Absolutely.
We're going to explore how these dynamic Markov blankets might help us to understand some of the biggest mysteries of the universe. From the emergence of life to the future of AI.
It's going to be a wild ride.
It is. Yeah.
Buckle up.
Buckle up.
All right. So before we jump into life and AI, I think it's worth spending a little more time with this idea of the ontological potential function.
Yeah.
It's really at the heart of what makes this paper so interesting.
I agree. It's a big one.
It is.
So we know it's related to like minimizing surprise, maximizing caliber within the boundaries of a system.
Right.
Can you give us a concrete example of how this function would work?
Sure. Imagine a school of fish.
Okay.
Darting and weaving through the water. At first glance, their movement might seem random.
Yeah, totally chaotic.
Right. It would be almost impossible to predict where any single fish is going to go next.
Yeah.
But what if we could find the boundaries, the Markov blanket, that defines the object of the school itself?
Okay.
Not the individual fish, but the collective.
So we're looking at the whole school as one thing.
Exactly. And when we do that, we start to see patterns emerge.
Okay.
The school has a certain shape. It moves in a coordinated way.
Right.
It responds to predators as a unit.
So even though each fish is kind of doing its own thing, the school as a whole has some order to it.
Precisely. And that's where the ontological potential function comes in.
Okay.
It describes the rules, the code, if you will, that governs the behavior of the school.
Okay.
It tells us what the school needs to do to maintain its identity, to stay cohesive, to avoid being eaten.
So like there's some invisible force that's shaping the whole school.
Yeah.
Kind of like how gravity affects the planet.
Exactly. We can't see gravity, but we know it's there because we can see its effects. Same with this ontological potential function.
We can't see it.
Right.
But we see what it does.
Exactly.
So if we can understand this function, we can start to predict how a system will behave.
Absolutely. And that brings us to the exciting possibilities of this framework for understanding things like the origin of life and the future of AI.
Okay, let's start with life.
All right.
How do we go from schools of fish to, like, what makes something alive?
Well, remember how we said the Markov blanket is all about information flow?
Yeah.
Well, life is all about information processing.
Okay.
Living organisms take in information from their environment, they process it, and then they use it to survive and reproduce.
So life is like a big, complex Markov blanket.
That's a really interesting way to put it.
Okay.
Now imagine the early Earth.
Okay.
Just a chaotic soup of chemicals.
Right.
What if certain molecules, just by chance, started interacting in a way that created a stable flow of information, a primitive Markov blanket?
So they made a boundary between themselves and the chaos.
Yeah, and once that boundary was established, they could start minimizing their free energy.
Okay.
Start adapting to their environment in a more organized way.
And that's how we got the first life.
It's a compelling hypothesis.
Yeah.
And this ontological potential function could be the key to understanding how that happened.
Wow. So we're saying that life is basically information processing and maintaining this boundary.
That's the beauty of this framework. It connects all these seemingly different things together.
Okay, speaking of connections,
Yeah.
how does this all relate to artificial intelligence?
Okay, so if we think of life as this complex system defined by its Markov blanket, then AI can be seen in a new light.
Okay.
What if instead of trying to copy the human brain perfectly, we focus on creating AI systems that can process information and interact with the environment just like living organisms?
So it's not about the structure of the brain.
No.
It's about what it does.
Exactly.
Okay.
And this ontological potential function could be the tool to help us do that.
So we could design AI that actually interacts with the world in a more natural way.
It's a bold vision.
Yeah.
And there's still a lot of work to do.
Of course.
But this framework gives us a possible path.
That's pretty cool.
It is.
Well, before we get too lost in the future of AI, I want to bring us back to the paper and some of the examples they use to show these dynamic Markov blankets in action.
Yeah, they applied their algorithm to everything, from a Newton's cradle to the Lorentz attractor.
Okay, so let's dive into those examples.
Let's do it.
And see how this all works in the real world.
Yeah.
So we've talked about this new way of defining objects with these dynamic Markov blankets.
Right.
And how it could explain things like how life began or how AI might work in the future.
Yeah, some really big questions.
But how does it actually work, in practice?
Right.
The paper gives some really interesting examples, like starting with Newton's cradle.
Yeah.
You know, those 5 swinging metal balls. A basic algorithm might just see those as one object.
Right, you would think.
But with the dynamic Markov blanket approach, it actually picks out the moving balls as the object and the stationary ones as the environment.
Makes sense.
Yeah, we instinctively kind of focus on like the action, the moving parts.
The transfer of energy.
Yeah, that's where the interesting stuff is happening.
Exactly. And what's even more interesting is that the boundary itself, the Markov blanket, only really exists during the impact.
So it's like the interaction creates the object.
Exactly.
Wow.
It shows you just how dynamic these boundaries can be.
Okay, so they also tested the algorithm on a burning fuse.
They did.
Which we talked about earlier.
Right.
The flame is always changing.
Yeah, it's constantly in motion.
Yeah. So how did the algorithm deal with that?
Well, it did a great job of tracking the combustion front as it moved down the fuse.
Cool.
It identified the burning part as the object and the unburned fuel as the environment.
So even though it's changing all the time, it can still tell what the flame is.
Exactly. It's all about the information flow.
Okay, very cool. What about a more complex example?
Yeah.
They used the Lorenz attractor, right?
They did.
That's famous for being chaotic.
Yes, it is.
So how did that go?
This is where things get really interesting. So the Lorenz attractor is this set of equations that create this trajectory that kind of looks like a butterfly.
Okay, I've seen that.
Yeah, and it looks random, but there is actually an order to it.
Okay, so what did the algorithm find?
Well, it essentially identified what we call a phase transition.
Oh, yeah?
Like when water freezes into ice, that's a phase transition.
Okay.
The algorithm labeled different parts of the trajectory as either the object or the environment, based on which wing of the butterfly it was on.
So even though the whole system looks random, it was able to find these distinct objects.
Exactly, by looking at these subtle changes.
Wow, that's amazing.
Oh.
It's like finding order in chaos.
It really is. And it makes you wonder what other systems out there might have these hidden layers of organization.
Yeah, maybe even our own brains.
It's possible.
Well, this deep dive has been a real trip.
It has.
We've gone from just trying to define a thing to talking about life intelligence.
The universe.
The universe.
Yeah, pretty much everything.
And now we have this new tool, these dynamic Markov blankets. To help us understand all of it.
It's like a new way of seeing the world.
It makes you realize that everything is connected.
Absolutely.
And that brings us to a final thought for our listeners. If we can define objects by how they interact with their environment, does that mean the environment is just as important
That's a good question.
as the things in it?
Something to think about.
It is. Thanks for joining us on this deep dive.
Absolutely.
And we'll see you next time.